what's better in a lot of cases is to use standard response curves. It's better in some ways. It's kind of, I guess what you call is the quick and dirty answer. So long as you understand how to manipulate them, you can use standard response curves to get an answer. And they look like that. And what I've got here is a family of curves for different values of zeta. So if I was to say to you this, and all these axes are normalized. Okay, so all normalized around a final value of 1, and the time axis is actually not time at all, it's time times natural frequency omega n. So if I was to ask you, what zeta do I need if I want to achieve an overshoot of 30%? What would you tell me?
4.45-ish.
That's a bit accurate, isn't it? 4.45-ish. Yes. Is it? No, actually, sorry. No, it's not. 30%.
0.35-ish?
0.35-ish, isn't it? It's the other side.
Yeah.
So if I wanted a 30% overshoot on these normalized axes, that takes me to a 1.3, which is somewhere between my 0.3 zeta and my 0.4 zeta. Have a stab, 0.35. It's obviously not very accurate, but it is useful. I want to reach my peak overshoot after 10 seconds. What omega n should my system have? Well, there's peak overshoot. Well, we were on a curve down here somewhere, weren't we? Peak overshoot, read down to the omega n times time. I want time to be 10 seconds, so I can choose omega n to suit. Okay, so you can get some reasonably good quality solutions if you can use the standard curves sensibly. So I've spent the last hour going through a whole bunch of mathematics with you guys just to show you this graph that pretty much says, well, you don't always need to do that. Okay, sometimes you can just, and these curves, by the way, will be attached to the data sheets on your exam paper, so familiarize yourself with them, because there's a lot you can do with these. You can't get the accuracy, but you can get a pretty good idea of what's going on.